So we've been looking at the definition of a definite integral, but I want to talk about also just interpreting the definite integral in terms of area. So instead of using the actual limit definition, let's see if we can reason geometrically. And we did that in one of the examples. We sort of looked at the graph and talked about how that would represent the integral. And let's take a look at some examples. The integral from -2 to 3 of the absolute value of x, right? If I graph the absolute value of x function, I hope you remember what that looks like, right? Looks like a letter V here, right? And it's always above the x-axis, because when I take the absolute value of any real number, positive or negative, the output's always positive. But here we're going to be evaluating from x equal -2 to x equal +3. Since the function f of x, which is the absolute value of x, is always greater than or equal to 0 on, well, all real numbers, but in particular on this interval, then what do we say? That the definite integral represents what? The area under the curve, which in this case is just these two line segments, from -2 up to 3. And so if you think about it, we've got essentially the areas of two triangles. Areas of two triangles. And so the value of this is what? The area of this triangle, which is 1/2, the base is 2, and the height is 2. Right? So that's sort of that portion, plus what? The area of this triangle, which is 1/2, the base is 3, and the height is 3. So I get 4, I get 2 here, and I get 9 times 1/2 is 9/2, or 4.5, which is 6.5. And there's the definite integral. Now, this is a way we can interpret it, right? If we can think about it graphically. We're not going to be able to do a lot of definite integrals this way because we're not able to get shapes like triangles and rectangles and things. Let's look at this one down here. The integral from -1 to 1 of the square root of 1 minus x squared. Now I've graphed the function here. I don't know how many of you recognize that this is the top half of a circle whose center is at 0 and whose radius is indeed 1. And if you think about the relation, if y is equal to the square root of 1 minus x squared, just think about where this came from. If I square both sides of this equation, I get y squared equals 1 minus x squared. If I add x squared, I get this. And you should recognize this as the equation of a circle. It's the equation of a circle with center at the origin and a radius of 1. So I hope you remember that from algebra. And so, but the value of y here, when we look at it, the root is always the positive root, so the output is always positive. We're only getting the top half of the circle. In order to get the bottom half, if I were to solve for y here, this would be plus or minus the square root of 1 minus x squared. So the bottom half would be negative the square root of 1 minus x squared, but we're just looking at the positive one. But at any rate, here's the graph, and from -1 to 1, we see clearly that this represents what? The area under this curve, because the function over this interval is indeed positive. So I just need to find the area of what? A half circle. So this is going to be 1/2. The area of a circle is what? Pi times the radius squared. And what's the radius of this circle? The radius of this circle is 1, right? The radius is 1. And so it's pi times 1 squared, which is just pi, times 1/2. It's pi halves. And there's the exact value. Okay, so that one we're lucky we're able to get a circle, or half circle, and be able to interpret it. But again, most of the problems we're going to do are not going to be able to be done this way. Some of them can be done this way, so it's nice. But you can always, estimate things too by looking at the graph and then in evaluating the definite integral. Here's another one: the integral from 0 to 8 of the function g of t, and the graph of g is given. So notice g is made up of piecewise defined linear functions as we go from left to right. We don't have to find the actual equations for these. We don't need to do that. We're going to interpret it in terms of area. And so notice that from 1 until 6, the function has positive values, right? So we have positive values. And I'm going to break up this region above the x-axis into 3 regions. See if this makes sense. From 1 to 2, from 2 to 4, and from 4 to 6. Does that make sense? Because in each of these regions, I've got a triangle, a square, and then a triangle. And I'm going to write plus in each of these regions, indicating that the area we get, the value we get, will be positive. But remember, it's from 0 to 8. So what about from 0 to 1? So notice from 0 to 1, if we go there, we've got this triangle here. But remember what's going to happen. The Riemann sum, the value of the function at the c sub i's will always be negative. So when we do that sum, we're going to get a negative value. So the integral will evaluate from 0 to 1 as a negative this area. Okay, area is always positive, but the integral will calculate whatever this area is of this triangle, but it will be negative. Same thing over here, right, from 6 to 8, and I'll split it up into two, right, this little triangle and this little square. Okay, so with that, we can say that this first region is negative 1/2, the base is 1, the height, if you will, is 2, and then what? This one is plus 1/2, base is 1, height is 2. Essentially, you're going to see what's happened to these two quantities, right? Essentially, they're going to cancel each other out. It'll be 0, right? Because this area down here is the same as this area down here, but the definite integral counts this as negative and this is positive. The next is the square, right? So what's the area of a square? 2 times 2, or 2 squared, right? Height and base are the same. And then this triangle has a base of 2 and a height of 2. And then the small triangle has a base of 1 and a height of 1. And then finally a square, which is obviously just 1 squared, or 1. Okay, so I mean I've basically broke it up into 1, 2, 3, 4, 5, 6 regions, and here's the area in each of those. The negatives, right, correspond to when the graph is below the x-axis, the positive when it's above the x-axis. Now we just can compute this. This is negative 1, this one's plus 1, 2 squared is 4, 1/2 2 is 1 times 2 is 2, this is 1/2, and this is minus 1. If you add all that up, you'll get a quantity of 4.5 or 4.5. Okay. And it kind of makes sense that the integral is positive. The negative, so-called negative areas, are less than the positive areas. So when we take the positive and subtract these negative areas, we get the 4.5. Okay, so that's how the definite integral works. It sort of accumulates negative area when the graph is below, but positive area when it's above as we move from left to right. And of course, that's why we can have the value of a definite integral be negative or 0. Okay? All right, so that's interpreting the integral in terms, the definite integral in terms of area. In the next video, the last video on the definite integral, we will look at some other properties of the definite integral.